So first of all, the plan is to do a full linear algebra lecture, meaning 3 academic hours. We give up on Infinite today, we'll continue it from the next Sunday. So it's a total of 2 hours and 15 minutes, 3 academic hours. So we're gonna have, let's say, 75 minutes studying, and then 15 minutes break, and another hour of studying, so fun, and we'll finish at 4:30 o'clock. A bit of introduction. You did linear algebra 1, it's very fun. We're going to continue with this fun. And everything I said about all the technical parts of course, it's applies as well to linear algebra 2. We don't have a midterm exam. We do have homework assignments, and here is in charge of that. Discussion about it. I want to submit the homework late, etc., etc. Talk to Neil. And practice. Do you already have linear algebra practice? No. No. Looking at my drive folder, you won't see linear algebra 2 lectures because I haven't put it yet here in Babylon. So I use a D, this lecture from this semester from the students' drive. Lecture, I'm going to try to follow these notes. So then again, if you don't want to come or something like that, you can always look there and study material on your own. We record, yes, it will be recorded, yes, and the recording is going to YouTube, usual. You will see one of my lectures or not. What? Monetize it.
Don't you put ads or markers as in it?
No, YouTube put ads. Either way, I'm totally fine with it. I'm totally fine with it because I have there, let's say, thousands of videos, at least 4 terabytes of videos, probably much more, and storage is free. Don't pay any shekel. If you wanna pay for some storage, services, cloud services for 4 or more terabytes, at least 400 shekels per year, something like this, something like that. So it's free because we are the product that's in the video. So it's I'm fine with this collaboration. Let's see exactly what I'm looking for here. So, any questions before we actually start the material? So fine. So yet again, I'm trying to follow D notes from last semester that actually okay. And we start with definition. Of course, I write from left to right. Start from the definitions. That is, from first look, doesn't look very connected to linear algebra, but as we continue, we'll see when the matrices show up. So our definition is permutation. Permutations. In here it's called muvot. 1 to 1, many to 1. The definition is simple, but we will discuss further interesting information about it. Say A is A of capital bijective 1 to 1 bijective function. We use the Greek letter sigma here. Little sigma. We have the big sigma for sum, and little sigma for permutation. Sigma from the set 1 to n to the set 1 to n is called permutation of n 1 to n. We know what bijective means, we know what 1 to n means. First of all, I want us to look at different ways to write down permutation. Put it on board, paper, and use to write. So we have, well, there are different ways to write, express a permutation. Let's have a list. 1, 2, 3, A, B, C. How do you prefer? Something, right? You have opened the Zoom, right? So we actually don't know. We give us subjects. I can hear Zoom. That's always fun. We can. אני צריך לדבר, עכשיו אני לא שומעים אותי. בסדר. Okay, so different ways of writing a permutation. First of all, we can write it explicitly, tell every component of the set what's its image. Exact word. For example, that's how we actually write functions when it comes to small sets such as 1 to n. Let's say 1 to 3, 2, 1 to 3. Defined by, I don't know. 1 goes to 2, 2 goes to 3, and 3 goes back to 1. 3. Yeah, it should be projected. Second way to write it down is a matrix of 2 lines, 2 rows. In the first row, we write the elements of this set, 1 to n. And in the second row, we write their images. So there's 2 rows. And then images below, beneath, whatever the elements. Example. Sigma from sigma 1 is 1 to 3, and 1 goes to 2, 2 goes to 3, and 3 goes to 1. It's different way to notate it.
This is
What?
this is a matrix, or is it like this? This is not the matrix of the function. This is just
No, yeah, it looks like a matrix, but we are not going to multiply it with another matrix or something like that, at least in our course. אני מדבר פה, שומעים אותי? So. More questions? Okay. Third grade, writing it down as big A, whatever, multiplication of let's call it cycles. Great. What a cycle is? cycle is a permutation in which, where, it's okay not to say. Every number is sent to the next one. Not in the set itself, not 1 to 2, 3 to 2, 2 to 3, etc., but generally to the next one in the cycle, line, and the other numbers go to you. It's a very nice set of words. Let's write down two great examples for that. Yeah. So first of all, for example, sigma from 1 is 1 goes to 2, 2 goes to 3, and 3 goes back to 1. So the name cycle is very appropriate. Let's say another example. Forgive me if I use a capital letter and never do it. Another example, let's write it down left. Yeah.
Sorry. For example, sigma from 1 is sigma 1 to 3, you mean 1 goes to 2, 1 goes to 3.
Come again?
And in this example, sigma is 1 to 3, you mean 1 goes to 2, 1 goes to 3, and 3 goes
And 3 goes back to 1.
Yeah.
Yes. Let's say, let's look at the bigger example. Let's say 1 goes to 4, 4 goes to 6, and 6 goes to 1. Let's say 2 goes to 3, and 3 goes to 2, 5 to 7, each. Which one is going to south? Writing it down in the way of multiplication of cycles, we get 1 goes to 4, 4 goes to 6, and 6 goes back to 1, so that's one cycle. 2 goes to 3, 3 goes to 2, that's another cycle. And when a number goes to itself, we don't have to write it down. One can write something like one can write something down something like, okay, we have 5, and that's all, and 7, that's all. But it's unnecessary, so I prefer to give up on it. The problem, one thing missing from this kind of notation is if we don't know what the big set is. I mean, it's 1 to 6, 1 to 7, 1 to 30, but every number above 7 just goes to itself. So we don't know what is the big set from this notation itself, but usually we get in the context, so it really doesn't matter.
Sorry, I don't.
Yes.
I don't understand. You say those two are equivalent,
Yes.
and how?
With one difference, here you can tell that the big set, the original set, is 1 to 7. Here you can't tell.
But how is it a permutation if 5 goes to 5 and 7 goes to 7?
A permutation doesn't necessarily have to send every number to a different number.
Okay.
Permutation is a bijective function. For example, the identity, every number goes to itself, is a permutation. A bit boring, but a permutation, nonetheless. the cycles more precisely. I mean, you can do it generally, but more precisely, we are looking a way to write the permutations down where the cycles are totally different. In Hebrew, zarim. Don't know how to say it in English. It means don't have any number in common. It's totally different numbers in the cycles, and this way is very compact. Just a couple of numbers, that's it. But we have also the way of two rows, and sometimes needed to tell everyone where it goes explicitly. It's more convenient. You can understand it better. So this is a permutation by checking function from one way to one way. And three ways to write permutations down. Questions? Okay. So we continue with that again. I want to follow these notes so we can have it very nice and well ordered. With the notes, the set of all permutations of 1 to n with Sn. Not exactly why the letter S was chosen. Sheesh! Exactly why. But that's the computation, not just mine. For example, you're looking at S2. By ejecting functions from 1, 2 to 1, 2, you only have two functions. As such, first of all, the identity, 1 goes to 1, 2 goes to 2. And secondly, the permutation that sends 1 to 2 and vice versa. When it comes to S3, you got 6, and we'll say shortly how many permutations generally in SF. But let's write down explicitly all the permutations in this as well. First of all, identity, one goes to himself. Then we have the permutation of 1 goes to 2, 3 stays in this place. We have 1, 3, and 2, 3. Similarly. And we do have the permutations of, let's say, a full cycle. 1 goes to 2, goes to 3, and 3 goes back to 1. The annotation stuff. And we have 1 goes to 3, and 3 goes to 2, and 2 goes back to 1. And these are all the permutations of 1, 2, 3 as a set. Generally, we have n factorial, let's say n factorial permutations in Sn. Let's write it down. It's a combinatorial question. It doesn't belong here. It belongs to discrete mathematics. You've already studied and did that, right?
Yeah.
Yes. Well, it's a question for Peter. Let's leave it there. Note. Absolute value means here the number of elements equals is n factorial. We count all the functions, not just bijective, with the difference n to the power of n. When you count only the bijective ones, permutations, it's n factorial. Question? Questions? Okay. Let's move on. Here we define the permutation itself. One can define the sign permutation. in order to define what a sign is, we need to define, we need another definition. Let's call it change order. Don't know what how to put it in my words. Here it's in Hebrew, it said, חיוב סדרה. לא יודעת גם ככה בעברית, כן? The question to it again. Just click. Change of order. I think it's good. What is there's a permutation. No. Sorry, that permutation where I smaller than j, sigma I is actually greater than sigma j. No, I want to write it down a bit differently. Sorry for that. Firstly, so I write it down then. Let sigma be a permutation. Sn is the self-permutation as we mentioned. If I is smaller than j, but sigma I is larger than sigma j, we call it change of order. For example, for instance, in sigma from 1 to 3 to 1 to 3. Defined by 1 giving 2, which means write down explicitly, no shame of that. Can you see it well? The orange one? So the answer is no.
I can see it.
It's another color.
I can see.
I should have brought the new blues for one car. Maybe we on the break, but we are purple now. Purple is good. Sigma 1 is 3, sigma 3 is 2, and sigma 2 is 1. In this sigma, we have two change of order. Changes.
Sorry. It's not a necessity that the original order is the trivial order.
No. I mean, one is smaller than three.
Yeah, it doesn't. It's not necessary that the range is on the trivial order 1, 2, 3. It can be 1, 3, 2.
Yes.
Okay.
Just a different permutation. Let's check it. We do have two. Let's write it down explicitly. One is smaller than 3, but no, sigma 1 is larger than sigma 3, so that's a change of order. 3 is larger than 2, and sigma 3 is larger than sigma 2. That's the order that is not. And lastly, 1 is smaller than 2, but sigma 1 is larger, greater, greater than sigma 2. So that's that change of order as well. So we do have 2 changes of order in this permutation. Call it a change of order. Now, after we found what change of order is, we can define what sign permutation is.
Yes, sorry. So the original, before we use the function to transform the values, there's no order because it's a set, right?
Yeah.
So it's the trivial order, always. Now, what confuses to me is that you're comparing the numbers and then comparing the resulting values. But first it's the trivial order and then it's the new order.
No, in both of them it's the trivial order. 1 is smaller than 2, 2 is smaller than 3, etc. But we look at the images of the original values. And we look at the images and say, okay, does the images, it's what you say, keeping the order or turning it upside down?
Yeah, so
turning it upside down.
This is nothing to do with position, it's all about value.
Yes.
Okay.
Yes, yes. More questions? Now, how do we define the sign of permutation? As usual, the sign can be plus or minus. In different words, 1 or minus 1. And we define the sign of permutation as minus 1 to the power of the number of changes of order. Let's write it down. Now, sign of permutation. Sigma is denoted very original notation, sign of sigma. It is minus 1 to the power of k, where k is the number of changes of order in C. So, for instance, sine of 1, 3, 2 is minus 1 in the power of 2, because we have two changes of order in sigma. Minus 1 to the power of 2 is, of course, 1. You know what? Let's write down the sign of every permutation in S3. For practice, it's not bad.
The two switches is 2, 3 is not a switch, but 3 to 2 is and 2 to 1 also, right?
Yes, you're right here. For every pair of elements, we ask ourselves, do we have this on the switch or not? And we count the numbers of yes answers on V against X, whatever. So here it is 2. Let's write it down. Yeah. And similarly, want to check the sign of the identity permutation. 1 goes to 1, 2 goes to 2, 3 goes to 2, 3. Now we'll change the order. So it is 1. If we consider the sign of the permutation 1, 2, yeah, which means, so write down in a big color. Considering 1, 2 means the sigma 1 is 2, and sigma 2 is 1, and sigma 3 is 3. So here we have 1 is smaller than 2, but sigma 1 is greater than sigma 2. So that's a V, that's the change of order. 1 is smaller than 3, and sigma 1 is smaller than sigma 3. That's not a change of order. And similarly, 2 is smaller than 3, and sigma 2 is smaller than sigma 3, which again is not change of order. So we have only one change of order here in this permutation. It's -1 to the power of 1, which is -1. And let's just write it down. The different signs of all the other permutations here in S3. If you take another such permutation, but that's just 2 numbers, you'll get the same result. You'll get -1, and write it down as well. Want to waste the board? First the board. The sign of 1, 2, 3 is 1 squared. So we have permutations, and we have this definition of sign of the permutation, of sign permutation. There are equivalent ways to define this sign of permutation, so that's the way I wanted to do it. Again, it's how we did it in the handouts, and I think it's the most simple way. I mean, SN permutations, it's a very important, very, I don't want to say basic, it's basic, but very important mathematical notion. It's well researched, well discussed. Sunday, we finished our Einstein course. The next lesson in this class, this room, was group theory for permutations. And the group theory doesn't matter what the group actually is, mathematics. The SN is very, very important, very, very, I don't want to say it's the center of course, but it's one of the most important examples for a group. Here, don't want to discuss it, the subject itself, just as a preparation for what's coming now. So I don't want to have a full discussion about the definitions of the sign, of the permutation, etc., etc. What we wrote is very nice. You take photos, send to father, very nice. But that's all. We use this, of course, in the next definition. which the first one, this lecture, actually looks like linear algebra. Before we move on, questions?
The only way to know this sign is to go one by one on over all of the permutations and check.
When one can conclude that the sign of a cycle is -1 to the power of the number of its elements, -1. You know what? Let's write it down. Let's write it down. I didn't want to, but you asked, so here we are. Notes. The sign of a cycle with k elements is k-1. These 1, 2, 1, 3, 2, 3 are cycles of 2 elements, so their sign is -1 to the power, of course, not k, but -1 to the power of k -1, -1 to the power of 2 -1, it's -1. 1, 2, 3, and 1, 3, 2 cycles with 3 elements, their sign is -1 to the power of 3 -1 of 2, which is 1 in the bottom line. And when you write additionally, in addition, the sign function, we enter a permutation, take a number, -1, 1, is multiplicative, which means the sign of the multiplication of 2 permutations, specifically 2 cycles, let's call them sigma and tau, under a Greek letter, it's sine of sigma and sine of tau. Because without proving, here we can say something like that. You want to calculate the sign of permutation, write the permutation down as a multiplication of totally different cycles. Then write down the sign of every cycle, which is easy peasy, lemon squeezy, right? Mathematics is generally difficult, lemon difficult. Here it's just k -1, put it in the power of -1. And then you can have the sign of the permutation itself. Just multiply the minus or +1 to get the sign. For example, the sign of a permutation we looked at earlier. Let's say 1, 4, 6, and 2, 3, or something like that, whatever. It's the sign of the 1, 4, 6, and the sign of the 2, 3. This is -1 to the power of 3 -1. This is -1 to the power of 2 -1. And the bottom line, we get -1. Writing it down looks easier. Yes, it looks like an easier way to calculate the sign. I agree. Problem is that it depends on 2 non-trivial propositions. One, the sign of the cycle is that, and secondly, that the sign function is multiplicated. But once we agree, you handle me as it's true. So one can actually calculate the sign of permutation that way. And if you do, that's true. You can have a go at it. I allow it.
Are there any exceptions to this?
What?
Are there any exceptions to this?
No. It's true. Whatever permutation we'll talk about. process of finding the different, totally different cycles that proposing our permutation might be exhaustive. Small numbers, this way, that way, it's never too long. More questions? No. Okay. It's nothing soon. Atara, how are you? Can you hear us?
Yeah, I just thought Archie joined. I didn't realize she didn't know we were having class.
Okay. So there are not so many, but different students
Atara understand me?
between linear and algebra.
Yeah.
Between the infinite and algebra.
Atara is an exchange student, so she needed calculus in the US. They do linear in the third year or something.
Okay. Should we hear this one as well? Most people on these used in my high school game. When that's mathematics. Okay, so let's continue on games. And now we're going back to matrices. In algebra, we have to have matrices. So our definition of determinant probably needs us to remind figure 2 from first year, so I'm not doing it right now. In Hebrew, it's not a Hebrew word, of course, but we call it determinanta. There's a female. Don't know why. It's determinanta. First of all, that is a reminder. For matrix A and the set of all matrices with elements from field F with m rows and n columns, we denote the element in the ICJ spot, row I column J with A and J, or real A is rep name with IJ like that. Someone's taking shopping. Maybe he's taking a shower. Actually, I had this thought this morning. Let's say I want to have a school badass. Having some exercise, my free time. Do I have a place to shower here in university? Don't know.
If you're creative enough, yes.
If you're creative, yes. Even if لما تحضروا شباب بس كان. There used to be, I don't know what about you, but you have your obligatory, mandatory, whatever the name is of courses, and your courses you have to take, but from your own choosing, some nice subjects, probably in your third year, and you have to take we call it the Judaism course. Yeah, very fun and games. It is fun. I did my first degree when I was in high school. So I was, I want to say stupid, I was naive. How did they choose my Judaism courses? I looked this up. First of all, of course, to now is that I can't go courses, not coming on my math courses, but if you do get in my schedule, I just look at the subjects, and if I found it interesting, I took the course. No, nothing, didn't check anything about how difficult the exam is, about do I have to be in class or not. Stupid as hell, just took the course because it was interesting. But it paid off. When I finished my first degree and then I went to the army, I had a call. Apropos, I was in the toilet when the call came, so remember it? Because it was in the Kiryat of Serbia. The Kiryat, there are many buildings. One of Tel Aviv, one of Matkal. It was in the Matkal building in the 14th floor, where the Matkal itself should be, because they had the best toilet in Hong Kong. So I was there, and I got my phone call, no, from an undefined number. I was shit, it's the Matkal itself. He knows I'm shitting in his own toilet, you're gonna beat me up. And I answered, it was like, hello, Elad, how are you? It's whatever from Judaism courses. You got very high grades in your Judaism courses. So we invite you to a ceremony where you get a nice te'uda. You are course of law, how do you say it? In Judaism courses. Okay, but no, I'm in the army. And there is a reward of 300 shekels, 3,000 shekels. I'm not in the army. I'm coming right now, I'm not in the army anymore. So, if you, I don't know if it happens, if it still happens, the ceremony with the nice confectionery and the reward. But if you do get some high grades in your first Judaism courses, think of trying to keep on track. Maybe you get the 300 shekels or 3,000. Yeah, three zeros after the 3,000. So that's the story of Judaism courses. You should choose them about how they are fit in your schedule, how easy they are, how the lecture is not a nagging one, not some assignments to the semester or stuff like that. But just remember that you may be rewarded if you did a good job. Okay.
He got so inspired from the story that he went to the shower.
What?
He got so inspired from the story that he went to the shower.
Right now, I'm a future. Well, to me, they were in most of them were actually interesting. But in hindsight, now I see students change their experiences from different Judaism courses. I wouldn't do it. Oh, it's interesting. You take it. Probably do what is the most easy one, the most quick one. Okay, let's back to math. We denote the element itself this way or that way, whatever flows will go. And now we can define the determinant. The determinant of the matrix A in F of N is denoted absolute value of A, or one can write as well that of A. Common sense. Semicolon. It is scalar in F. I mean, you enter matrix and you get a number. In F. And one can write that the det is a function from a set of matrices to the field itself. You enter a matrix and you get a number. And it's defined in a complicated way. We get rid slowly but surely. The determinant of A is the sum running all over the permutations in Sn. I want to correct myself. Here, Mn is good, but we talk about determinants only in square matrices. The number of rows equals the number of columns. One can think of generalizations of determinant to every matrix, but in our course, not right now. So, determinant is the sigma running all over the permutations in Sn, and you write down the multiplications of A1 sigma 1, A2 sigma 2, etc., etc. An sigma n. Revert. Fascinating, very good understanding. Let's write it.
Yeah, so
Huh?
what they have.
Yeah. But here, I don't know if I told you something, my main job, principal, to say, is not here. I'm a lecturer, formal lecturer, I'm just supporting the people in Khalid and of course, the level of study is lower, not much lower, but lower. It's easier there. So I don't define determinant like this. I define it with formula, calculating formula, which is more convenient. We'll get to it probably in this lecture, but let's roll and find out. And here, I want to keep on some level of teaching. So we define determinant as such. In every element, we take the index of the column to be the sigma row and multiply it, and we're going to sum it all over the permutation list, and it's 5. Now, let's take an example. In S2, we have 2 permutations, so we're gonna have 2 elements here to sum up, which is fine. In S3, we have 6, so this sum is gonna have 6 elements, which is okay. In I don't know, S6, it comes to 720 elements to add up. As I say, it's gonna be very fun, but we're gonna have as I said, formula for calculation, which is gonna be easier to use, and we're gonna have a lot of I don't know, propositions, sentences, claims that going to make eventually calculate the determinant easy. Yes.
Before we go to the exam, can you explain what the cat's going on here?
Yes, I think that an example will help you do it. Help you do so.
Yeah.
Let's look at an example and write everything down. So, for example, let's look at a 2-on-2 matrix. Call here elements A11, A12, A21, and A22. So when n is 2, no, what do you mean? Right, that's right. When n is 2, we have 2 permutations. One would be an entity. Sigma 1 is 1, sigma 2 is 2. And one can write an identity, ID as well, of course. And the second one sends 1 to 2 and 2 back to 1. Now let's denote them with different letters. Well, let's call it identity. Here's identity. Want to write I or something like that? Now, if I want to calculate the determinant of A, the determinant of A, determinant of A1, A2, 1, 2, A2, 1, and A2, 2. We're going to sum all over the permutations S2, A1, sigma 1, A2, sigma 2. We have two permutations in S2, so we can write it explicitly very easily. One permutation is the identity. Forgot something. Why did I forget? Just to make things complicated even more. Yeah, exactly. The determinant is not just the sum of all these elements, but for every element, you should multiply it by the sign of sigma as well. And add it up here. Sigma, so now, when I write it down explicitly without the sigma, I get -1 or sign of the identity permutation, A1 identity 1, A2 identity 2, plus the sign of the second permutation, which I call sigma, and A1 sigma 1, A2 sigma 2. Now, as we mentioned before, the sign of the identity permutation is 1, and the sign of this sigma, which is 1 change of order, is -1. Let's write it down with different color. Active.
This is the principle of inclusion exclusion parameter.
Just cheat here. Here, the identity of 1 is 1, the identity of 2 is 2. So we get A1, 1, A2, 2. Sigma 1 is 2, sigma 2 is 1. So we get here minus A1, 2, A2, 1. And this is the formula for the determinant when it comes to a 2-on-2 matrix. Multiplication of the elements in the diagonal minus multiplication of the other elements. Let's write down an example with actual numbers. And then I want to write it down explicitly for n equals 3 as well. Then we can go on break 15 minutes. Yes. Let's say numbers you love, numbers you like, number you want to watch on the board, numbers you love, give me numbers, man. Numbers.
8.
Wait.
8. 6. 22.
22?
Yes.
So, it's going to find A 22 minus 6 and 7. And that is a number. Yeah, I'm too old to understand the meaning.
Yeah,
of 6, 7. Huh?
No one understands here. We're past over things. That's
As older as they get, the age of understanding mean becomes younger. I mean, it's not just that I was 18 and now I'm 30. I mean, now I'm 30 and the age of mean understanding is 15. This goes down all the time. When it comes to that, for my grandchildren, or babies, they understand the things. So it's a number, whatever, you can calculate it and tell me afterwards.
176 minus
Yes.
42. 42. Wow.
It's not that important for me. What? That's irrelevant question, of course. Irrelevant. And what are we going to do with this determinant? Why is it so important? Why do we learn it? Why do we study about it? So we're gonna have this discussion, but not now. Not now, just now in the beginning, our first step. So just as an example of how to calculate determinant of specific matrices. So for a matrix of order 2, it's not that hard to apply this definition, and we get some nice difference between these multiplications of elements of the matrix. I want, as I said, to write down, or at least have the starting generalize of the formula we get when A is of order 3, using the definition, of course, of these permutations. Before that, any questions?
Because why there was sign of like and sigma of y, were they in the like what a one sigma one and
the definition is every index of row. The index of column is the sigma of it. So here, this specific sigma, this specific rotation, sends 1 to 2, vice versa. So sigma 1 is actually 2, and sigma 2 is actually 2.
Okay.
Yeah.
Because it's like exactly put us the sum, like every element appearing the sum once.
Every element,
Because I mean, yet again, maybe on a bigger matrix it doesn't work, but A11 appears only once, A22 appears only once, A12 appears only once, A21 appears only once. That is it always like
no. I understand the question now. No, let's write down the formula explicitly for matrices of order 3, and we're going to see that we're going to have every element more than just one time, but in every part of the sum, we have different elements. That's because sigma is by general. Okay. So what about n equals 3? We have 3 factorial, which is 6 permutations. And we write it down beforehand. The permutations and their signs. Let's write it down quickly. We have ID. We have, let's call it sigma 1, which is 1, 2. We have sigma 2, which is 1, 3. We have sigma 3, which is 2, 3. We have sigma 4, which is 1 goes to 2, goes to 3, and 3 to 1. And sigma 5, 1 goes to 3, 3 goes to 2, and 2 goes to 1. What? Identity, yes, write it down. Identity. Their signs, as we mentioned before, is plus, minus, 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 plus, plus again. So we get, let's write it here. So we have it in one frame. So we get determinant of A, which is explicitly A11, A22, A13, etc., etc. the sum of all the running all of the permutations of S3, the sign of sigma A1 sigma 1, A2 sigma 2, A3 sigma 3, and for the identity, the sign is plus, and every number goes to itself. So we get A11, A22, A33. In purple, we'll write the permutation that gave us this element in the sum. What about sigma 1? Sigma 1 is minus, and in sigma 1 is 2, sigma 2 is 1, and sigma 3 is 3. Remind you that when you write a permutation like this, 1, 2, where the hell is 3, means 3 goes to himself. So this is what we get from the permutation we denoted here, sigma 1. Sigma 2, something familiar. 1 goes to 3, 2 goes to himself, and it's yet again minus, because it's one checking border, where sigma 1 is 3, sigma 2 is 2, sigma 3 is 1. That is our sigma 2, left 4. Sigma 3, minus again. 1 goes to himself, 2 goes to 3, and 3 goes to 2. That comes from sigma 3. Now, sigma 4 and sigma 5 are plus. In sigma 4, 1 goes to 2, 2 goes to 3, 3 goes to 1. That is the element we get from sigma 4. And last but not least, sigma 5. Sigma 5 sends 1 to 3, 3 to 2, and 2 to 1. So we get 1, A, 1, 3, A, 2, 1, A, 3, 2. This element belongs to sigma 5. So, generally speaking, when you have a matrix of order 3, this beautiful thing, beautiful. You have this big, beautiful formula is the determinant of A. Why?
Why? Yes.
Why?
That's
Why? We're gonna have a full. It's an important basic notion in math. Determinant of the matrix is gonna be our companion, our best companion, best friends forever for all linear algebra 2. And when you enter more advanced courses, not just math, but machine learning, etc., you'll probably see him as well. But just the definition and how do we apply it when it comes to small values of n, 2 and 3. Okay. Questions?
many. Many, but none of which you are going to answer right now.
So let's take a break for 15 minutes. And of course, we take it quickly. I still think it's not really actually work.
Well, what was the thinking? Are you paying for anything right now? Because like a lot of students are paying for it.
Oh, by the way.
Okay. Okay.
Yeah, it's paying.
Recording is now in progress. What I'm gonna do now, so maybe a lecture, is to state some of the determinant properties and prove some of them, but of course not all. And the nice calculation formula, as far as I can see, we'll get to it, but not today. Why do we say to the god of nice calculation formulas? Not today. Next week. So, okay. So I have this plane. How do I say that now? Proposition, right? So doesn't feel like theorems. It's here. Proposition. First of all, there are specific cases in which the calculation of determinant is easy, even when it comes to the definition, the other definition with the permutations. So, if let's say let's A, F, and N be a triangular matrix. For the proof, I'm going to use upper triangular, but it's right to it's correct for lower triangular as well. Then the determinant of A is actually the multiplication of the elements of the diagonal, the ring diagonal. We use big pi for multiplication, just like sigma is for sum. So let's write it down specifically. It's 811, 822, etc., etc. There is an n.
Is it big pi or is it phi?
No, it's pi.
It's pi.
It's the same as the relation between the radius and the radius. Pi. And then the multiplication of the elements of the main diagonal. Want to continue here? Left to right, left to right. I have 7 English hours this semester and 15 Hebrew. It's also Hebrew. I need to remember left to right, left to right.
This is also your first time teaching linear algebra, like because I know you usually teach calculus.
It's my first time teaching linear algebra 2 here at computer science lecture. I taught this material in different places, not here in Bar-Ilan, or at least not in science Bar-Ilan. And I had practice 2 years ago or 3 years ago, linear algebra 2 practice here in computer science Bar-Ilan. Lecture, no, we didn't have it. Not in Hebrew, not in English, not in Farsi, not every other language. We can try to speak now. So, let's write an example. Purple. Numbers you like? 3. And what did you say earlier? The determinant is the multiplications of the elements of the diagonal. Okay. So people, you good? Yes. Let's prove it. Let's prove it, and then maybe we'll move faster. Not much proofs, so we can.
Because everything else is multiplied by 0, and like that's it.
Yep, that's actually the reason. But let's explain why. So proof. The determinant is the ugly sum we saw earlier. running a lot of the permutations, the standard permutation, A1 sigma 1, A2 sigma 2, etc., AN sigma 2. So, whatever it is, we have the identity permutation. The identity permutation gives us sign is 1, it's plus, so right? A1, 1, A2, 2, ANN, and all the other permutations, I can write it out that way. Sigma and Sn, and sigma is not the identity. Sign of sigma, A1 sigma 1, A2 sigma 2, blah, blah, blah. Now, that's actually what I claim. Every single element of the sum has at least one element which is 0 because the matrix is triangular. For our proof, let us assume that the matrix is upper triangular. It's all the same, more of the same when it's lower triangular. The elements below the main diagonal are 0. What does that actually mean? It means that when you take I, which is greater than j, the index of row is greater than the index of columns, you get 0. A21, A31, A31, A32, so on and so on. So the identity permutation takes every number to its set. Fine. Great. Every other permutation that has at least one number that goes to someone else. Different number. But because the permutation is a bijective function, if one number goes to a number bigger than it, there must be another number that goes to a one which is smaller than it. Let's say, for example, 2 goes to 3. Okay, 3 goes to 4. 4 goes to 6. 6 goes to 9. 9 goes to 10. Eventually, I get to a number that has to go back to the number to list. Someone has to go to 5. So part of the 5. And because of it, every single of these elements of the sum has at least one element of the matrix, which is 0. How do we write it nicely and formally? Yes. For sigma, which is not the identity, we have some I such that sigma I is not I. So if sigma I is greater than I, first of all, is smaller than I. A of I and sigma I is 0 because we assume that it's an upper triangular matrix. And all the element, because of multiplication, is 0. Not
There is a J.
yes. Let's write that. And so all the sigma, sign, sigma. 0. Otherwise, elsewhere. Sigma I is greater than I. Because, and again, sigma is the objective, there must be a J such that sigma J is smaller than J because sigma is bijective. So the element sine A1 sigma 1, etc., is 0 again. So every element of the sum set element that belongs to the negative permutation, the multiplication of the element when they are is 0. So the matrix is triangular. Calculating the determinant is very easy. Questions? Anyone writes it down? Yes. Well, write it down. This is the same. Right now, we know how to very easily calculate the determinant of a diagonal, not diagonal, not just a diagonal, but triangular matrix. We know when we're given a specific matrix A, we know how to take it to a triangular form. So exactly whatever is the question, but the Gauss elimination or whatever, we can apply some row operations in order to change the matrix from a general matrix to a triangular one. And then the calculation of the determinant is very easy. So we can ask ourselves the following question. How do elementary row operations affect the determinant? Let's say, I'll write it down in a short time, but let's assume that changing rows doesn't change the determinant at all, and multiplying a row with a scalar alpha, and multiply the determinant with a scalar alpha, and adding the multiplications of a row to another row, adds the determinant, multiplies by 2, whatever. So I can, in order to calculate the determinant of any matrix, I can use elementary row operations and get a triangular matrix. With every step, I can say how the row operation I just did affects the determinant, and the bottom line at the end with a determinant that I know how to calculate easily, as per multiplication of the elements of the main diagonal, and I know how I get to it from the original determinant. So if we only answer this, this question, how do elementary row operations affect the determinant? We can have our way and have I don't want to say easy, but I said easier. That's of course surely true. An easier way to calculate determinant. Even if the matrix is 4 of 4 or 5 of 5, not going to calculate 5 factorial elements, add it all up, calculate the size. Hashem Yerachem. I can use elementary row operations to get the triangular matrix and calculate hair determinant instead. So this is the question. Our next question. The next question. How elementary, what's it? Row operations. Oh. Effects with E or with A? A. Effects. Determinant. That's the title. So, first of all, I'm just going to write it down. Okay? And then we'll have an example, maybe even two. And then I want to write another 2 or 3 properties of determinants. And when we finish, look at the clock. If we have more time, we'll prove what we're going to prove till 4 and 3. So we have 3 types of row operations. Let's write down as a list. First one is changing rows, one with another, with denoting Ri and Rj. How does it affect the determinant? You put minus on the determinant. In other words, if we have I'll write it down there. Okay, it's better formulated that way. If we have matrix A and we change just one time 2 rows, we switch to 2 rows, we switch is a better word. When we switch to rows, the determinant of A is multiplied by -1. Okay?
You change the sign. Yeah.
Yes, so if we get matrix A from B by the operation of switching rows, then the determinant of A is minus the determinant of B. Again, in other words, switching rows, multiplying the determinant by 1. We can show it in a simple example. The determinant of 1, 2, 3, 4, as we already mentioned before the break, is multiplication of all that. The diagonal minus 3 and 2, which is -2. When you switch the rows, I claim that you get -2, which is 2. But let's see it on board as well. Switch the rows. By definition, multiplication of the diagonal minus the other elements, and how surprisingly, we get 2 is good. Minus of the original determinant. So, if for some reason I change the rows twice, so we have 2 switches in the rows, we get the original matrix. It goes minus is plus, the original determinant. So, why is it true? They said we do have spare time in the end of the lecture. I'll try to prove as many things and many properties as I can, but first of all, let's have properties themselves. We know them, we can use them in practice and homework. Then, as time allows us, we will. Okay. Second type of row operations is multiply a row with a scalar, let's call it alpha. So if we get A from B by multiplying a row with the scalar alpha, then the new determinant is the old one multiplied by the same alpha. Let's have an example here as well. Of course, it's not a proof. Example is what we have. We can take 1, 2, 3, 4. It's a good example. You can choose a scalar and a row. Go for it.
First, yeah, multiply by 3. First row multiply by 3.
Okay. 3R1 goes to R1. So 3, 6, 3, 4. Here the determinant is 2, A is minus 2, as we already mentioned. And here, by the formula, we get 3 and 4 minus 3 and 6. Oh, that's minus 6, which is 3 multiplying minus 2. Of course, the example is nice, but I can produce this name, whatever you want. That is generally true. Whatever alpha is, whatever n is, whatever row you choose. That is how multiplying a row by alpha changes the determinant.
That one the proof is easy.
But
That one the proof is easy.
yes, if we write it, we write down the formula, only one row is multiplied by alpha. So every element of the sum that defines the determinant, only one element is multiplied by alpha, which means that every element multiplied by alpha and all the sum of the determinant is multiplied by alpha. Yes. If I want to write it down, it's not going to be very complicated, but first of all, I said, let us finish all the, let me give you all the knowledge you need, and then we'll get to the proofs. What else to say? In Hebrew, there is the cake. Okay, the cake. You have the dough, you have the lavzane. How do you say it in English? Concepted.
Cream.
Cream. Cream is a good word, yeah. The cream, and then finally you have the strawberries or whatever. So first of all, let's just have the dough, the cake itself, and then the proofs. The strawberries above here. Okay. These are let's call it picture case. When we actually try to get a matrix to a triangular form, which was we did a lot in the first verse, and we're going to do it as well sometimes here, but not that excessively. When we're trying to use row operations to get a triangular form, we almost do not use these two types of row operations. If we are going to go to the canonical form, then multiplying by the appropriate scalars to get one on diagonal, but something else. But here, our proposition talked about triangular matrix. And in order to get a triangular matrix from specific matrix, we almost do not use not switching rows and not multiplying rows by a scalar. What do we actually use? Let's say 95% of the time. The third type of row operation is exactly adding a multiplication of a row to another row. So that's the money time. How does this type of row operation affect the determinant? And the answer is surprisingly nice. If you get it.
It doesn't.
It doesn't, yeah. if we get A from B by, let's write it down that way, alpha Ri plus Rj, Rj, then the determinant of A is the determinant of B. In other words, it doesn't affect the determinant, which is nice. Which is nice. We can statistically do most of our eliminations in order to get triangular matrix without using not one nor two type of rule operations. That's not free. And doesn't affect the determinant at all. So now let's have an example. Now we can, let's write it down explicitly. We can calculate determinant A with the elimination. We know how every row operation affects determinant, the determinant in the end, the determinant of the triangular matrix is easy to find. It is again the multiplication of the diagonal. So let's have an example. For instance, let's calculate the determinant of classic example 1 to 9. One can use the formula we got in the first part of the lecture, but let us show this way of finding the determinant, and when the matrix is bigger or uglier, it's probably the better way. As I mentioned, gonna be in the next lecture, we're gonna see a different way of calculating the matrix without row operations. And then we can have a discussion of which way is better. But right now, the way of using row operations is probably much better than writing down all permutations and their sign, etc., and jump on the window with the processing. So let us write the row operations we do in order to get a triangular matrix. Something we did a lot of times in the last course. And I am trying to stay only on paper. Well, let's make sure that it is. Whatever it is, it's for the bonus discussion. There's a lot. Let's have to say about something. So, I try to say, I'm going at least we're going to try, and use only this type of operation. So we know that determinant actually stays the same. And the specific operation I choose, you know, to do it better than me, we'll have R2 minus 4R1 into R2, R3 minus 7R1 into R3. Now you have to observe and correct me when I write nonsense. It is 0. 5 minus 4 times 2, it is minus 3. 6 minus 4 times 3, it is minus 6. 7 minus 7 times 1 is 7. That's why we chose this specific row operation. And now the collateral damage. 8 minus 7 times 2 is minus 6. And 9 minus 7 times 3, 9 minus 21 is minus 12.
Does this, I mean, does this work? You can make it triangular.
Yes.
You can.
Yes.
Okay.
Is this just Gaussian elimination?
Yes. Yes, this Gaussian elimination. We know to do. I don't like to call it the Gaussian elimination because when you get down to the Gaussian, it's a very well-ordered algorithm. When you have a column of zeros, put it to the left, and many times when we actually do the elimination, we don't go every step by the book of Gauss. We can, for a specific matrix, we can look at, you know, maybe here the operation of minus 3 and minus 6 is better than going by the book. So we're going just an elimination, but it is what it is. Right now, we can set minus 6 to heaven with minus 3 above it. One can write R3 minus 2R2 into R3. Yet again, you are observing that I am correct with every step. 0 minus 6 plus 0. That's why we chose this specific operation. And how surprisingly convenient. Minus 12, minus 2, minus 6 is minus 12 plus 12. It is 0 as well. And here, 0, not 0, doesn't matter. It is a triangular matrix. And when it is a triangular matrix, I can multiply the elements of the diagonal. And this is the determinant. Here, it is 0. And I can tell you right now, I can even explain it. But let's just say it right now. And after we finish what you want to say, we start explaining how much we get. That's what I already said. Determinant is 0 if and only if and only if the matrix is singular. It's not invertible. Here the matrix of 1 to 9 is not invertible. So we have determinant of 0. But one can say it more specifically when we have a row of zeros. When we have a row of zeros, the determinant is 0. Because in every element of the sum of the definition determinant, there is at least one element from every row. Because we write A1 sigma 1, A2 sigma 2. 1 is from row 1, 2 from row 2, and so on. So when there is a row of zeros, every element in the determinant becomes 0. So generally, in general, if A has a row of zeros, then the determinant is 0. And when it comes to singular versus invertible matrices, we know that what's the difference between them? That's by definition, but by the Gauss elimination, we actually apply an invertible matrix, when you use Gauss elimination, till the end, you get the canonical form of I. That identity matrix. On the other hand, when you use the elimination on a singular matrix, you get the row zero. So, if we start with a singular matrix, somewhere with the process, we'll get a row of zeros, so the determinant is zero. On the other hand, if we got a zero on the process, it means that we started with a singular matrix. So, I don't know if it's a moreover, let's say moreover. Not every singular matrix has a row of zeros. Every singular matrix does have a determinant for zero. True. Well, not invertible. There's no such A minus 1, not B, such A multiplication with B is 5, so on. One can say, because if it's if and only if A is invertible, if and only if her determinant I hope everyone's okay then. It's not zero. Okay. So what does one right now when it comes to properties of the determinant? More than this. First of all, on one hand, let us notice that the determinant is not a linear function. The determinant of A plus B, determinant of A plus determinant of B are not necessarily equal. It can be always. And the same is true when it comes to multiplying with a scalar. One can say, and maybe I write it down, the next property. What happens to determinant when you multiply all the matrix, not just one row, with a scalar alpha? First of all, let's give a counter example. That example, something very simple. Yeah, something like that. When we look for examples, doesn't matter what the subject is, they always should be as simple as yes. So when it comes to matrices, it should be 2 and 2 matrices, not more, and with a lot of zeros. And no, don't want the zero here. As you suggested, that's a good counter example. Here, every determinant is 0 because every matrix has a row of zeros, but when we first summing the matrices and then calculate the determinant, it is one because it's the multiplication of the elements of the main data. And of course, 0 plus 0 is not 1. However, even though the determinant is only given, it does not preserve some matrices. It does preserves the multiplication matrices. It's called multiplicative. Say it here or in some tables, function that preserves multiplication is called multiplicative. So determinant, however, determinant is multiplicative. The determinant of A and B is the determinant of A and the determinant of B, of course, when the determinants are defined. Meaning that you can take two not squared matrices, multiply them and get a square matrix, and then the determinant of A and B is defined, but every single determinant is not defined. As I mentioned, when we started the subject of determinant, we're focusing on square matrices only. So determinant is multiplicative. It's not complicated, but we need some steps in the way in order to put it correctly and right. Steps that we are not going to take this lecture. Maybe next lecture, maybe no. We had a couple of minutes of delay at the beginning. Nice stories about the shop stuff by the F toilets. So maybe not putting everything. I think so. I want to write what I mentioned earlier, what happened when you multiply all the matrix with scalar alpha. Before that, any questions? Zoom people? Zoom guys? Zoom ins? Yes. Any question? We may guess. Ask the question. Question the question. Don't have a verbal question, right? So, another property. Of the determinant if A is a matrix order n, then when you multiply A by scalar alpha, the scalar goes out to the power of n, which is very easy to understand after what we said about the row operations. The multiplications of single row with the scalar alpha multiplies the determinant with alpha. Say we have, for example, three rows, and when you multiply the whole matrix with alpha, you multiply every row with alpha. And when you have three rows, you multiply the three rows with alpha, it's three alphas that goes out. Goes explicitly. Because we have n rows and every row multiplied by alpha multiplies the determinant by alpha. So assuming that what I said earlier is true, it is true, but we didn't prove it yet, and we are not going to do this lecture, we're going to do Python. Then you have a lecture, not so bad, but putting every
Not everything is proof. We can't just accept how it is.
Yes, I always say if, generally speaking, I wanted to prove everything I said every course, I probably would need 2.5 times of lectures / practices that I have now. Let's say we have 3 hours, 8 hours every week for 13 weeks, something like that. If I want to need to prove everything I say, I probably need something like 7-8 hours. It applies to every mathematical course that I teach and I study. Questions? Okay. So in this short time, I'll give you these notes. The main propositions and claims. I've already said some things are very simple or it's relevant. So in our little time, we can prove 1 or 2 of the things we already said here. Let's prove let's write another property of the determinant, and then we'll see if we have another minute or 2 to prove something. Because some of the proofs, as you already said, pretty easy. Everything is multiplied by a, such as that. Another property. The determinant isn't continue from here. The determinant is not linear. However, we can tell that it is multiplicative, and we can tell what happens when you multiply matrix A, and there is some kind of linearity when it comes to determinant, not the regular one, but the determinant is what I call him row linear. What do I mean? Right now here. Let's write the matrix explicitly like that. The first row is V1, second one is V2, blah, blah, blah. And in the I row, we have something like V plus U. And then it goes to the N row. I write down exactly the way, great. Be not afraid. We can write it as the sum of 2 matrices, where one matrix has V and the other one has U as their I rows. All the other rows stays the same. For example, let's say we have the matrix of 1, 2, 3, 4, 5, 6, 7, 8, 9, and the matrix of 1, 2, 3, 3 minus 1, 2, 7, 8, 9. We can add it up to one determinant where the second row is the sum of the second rows here, and then 7, 4, and 8. So paired row, we can talk about linearity. So it's a no notion, not making it up right now. Determinant is what is called a multilinear function. It's not linear by itself, but if we look at it, we divide it to n functions that operate in each row separately, every such function is linear. We call it row linear. The proof here as well is not very difficult, not very hard. As you mentioned before, the proof in writing, but you say it very nicely. The proof for the A multiplied row, so every element is multiplied by row. Something similar happens here as well. In every element of the definition of the sum, we have one element from the row of V plus U, which you can separate to two different elements, one with the element from V and the second from the element of U, and you get the two different determinants here. Don't have much time for this proof. One can say that you don't have time at all. So it's good that we wrote down this property as well. I want to write down something tiny bitty and we can finish. Before that, any questions of the property or the example?
Yeah, I'm confused with it's not her, but it's like you have the same vectors for every row except
one row. Yeah. So it's easier to look at it maybe from that side of the equation. How two determinants become one. When every row is the same except one, we can write these rows, and in the problematic row, we add up different rows from between.
I mean, can you add multiple rows?
In the same operation of sum notation.
I mean,
This to be that type of sum. Every row is the same except one specific row. You can add up third matrix where you have V1, V2, etc., and here at W instead of V or V.
I feel like the most confusing part is that we started the class talking about permutations and design. Like we didn't talk about why design works like that. And we didn't we went into determinants and it's like an inherent part of matrices, so why is it important? Like we will talk about what we learned in the class, but we didn't really explain why it's important.
No, why it's important will come later, of course. But right now we are struggling with the definition itself of determinant.
Yeah, what is it?
Huh?
What is it? Why does it work like that? Why?
So, as I mentioned before, first of all, we're gonna see it. Secondly, it's gonna be our best companion through all the linear algebra 2, and you're gonna meet it in different places as well. Determinant is the basic notion of mathematics. It says a lot about the matrix, even though it's just scalar, the matrix is a lot of numbers. And thirdly, now we are, as I said, struggling with the definition itself. We already have a nicer, easier way to calculate determinant using the law operations. And if we want to prove what, as we said but didn't write, why the properties of determinant we discussed it today are true, we are using the definition. Every element of sum is multiplied by alpha, and whatever we said about these properties. So, right now, we stand here at the end of lecture 1. We have the definition of the determinant using these permutations. And we have properties of the determinant. First of all, I can say that this property has its importance. Let's say in the language of linear algebra 1, if you want to state for a given matrix that it is or it is not invertible, you have to start to eliminate, apply Gauss elimination, or using some fancy theorem / proposition from linear algebra 1. And here it's very simple. Being telling a computer to calculate the determinant is very easy because it's just this many for us human beings. The computer is chips calculating the determinant. It's many multiplications and adding up of numbers. So we have a different way, different approach, totally different approach to the question of does this matrix A is invertible? A different approach that it is much easier to command the computer to do so. I mean, Gauss elimination, as we mentioned, is in the end an algorithm. But us as humans, as we mentioned before, usually we're not following it step by step. We're looking we look at the matrix and we say, oh, yeah, right now it's actually better to do this operation, not that one. And we look at it and it's better to do. It's something that it's very difficult to say to the computer to write it down for me. And when it comes to determinant, it's actually pretty easy to calculate, to say to the computer, to order him, to command it, whatever word you want to use, to calculate the determinant. So if I take something for the why question from this lecture, it should be this line. Moreover, whatever I write here, how do I use the determinant to decide if a specific matrix is invertible or not? And as already said, through the semester, through the next lectures, we're gonna see a lot more of this little fella, the determinant. Okay, time is up a long time ago. Atara, do you have any questions before we close the Zoom?
Yeah.
Hardly. Okay, try it now. Try now to speak. No questions. Okay, it's fine. You said if